Okay, well, today let's begin chapter 2. Chapter 2 is resistive circuit analysis. Again, this is still material from your prereq classes, which is basically using resistors to control circuit currents, circuit voltages, and then we'll see how we can combine these resistors in series and parallel and use them to devise a technique known as series parallel equivalent analysis, which I believe is covered in your prereq classes, but I'll cover it here nonetheless. So resistive circuit analysis begins with resistors connected in series. Okay, resistors connected in series. Now, the first thing I would ask students is, how do you know if a component or two components are connected in series? Anyone put it in words? There is a junction, yes. There's a junction. More importantly, node is where two or more connections come together, right? Electrical junction. If a junction has only two components connected to it, then those two components are said to be in series. There cannot be more than two connections at a single node. So in this case, we have a connection here and a connection here. So in order for a series connection to be valid, you cannot have you cannot have any more than two. No more than two components at that junction. If you have a third or more than three connections, then it is not in series. So in order for two components to be in series, they have to be connected at one single node, and there cannot be more than two connections at that node. And you can have infinite components all connected in series. As long as every single connection in the middle or every component in the middle is connected in series, we can state that all components in that connection are in series between the outer two terminals. Okay. So when we have resistors connected in series, we can combine them mathematically to come up with one single equivalent resistance. We note it as REQ, REQ, R equivalent, and it simply is given as the sum of the three resistors in series, or basically however many resistors you have in series. If you wish to find the connection, let's say I'm going to call this node A, B, C, and D. If I wish to find RAC, meaning I'm measuring the resistance between A and between C, it would simply be R1 plus R2. RBD would simply be R2 plus R3. And REQ or RAD is simply R1 plus R2 plus R3. Easy enough? You all remember this, hopefully, right? Then one more point is, if you have a current I that is flowing through R1, logically speaking or logically thinking, is there any other pathway for that current to flow through? No, there's only that single pathway, right? So if it's series, the current always remains the same. Okay, if it's a series connection, have to keep in mind, the important thing is that the current that results is a result of all of these resistors acting together. Okay, when we say the current remains the same, it does not mean that if you add like 100 more resistors or 10 more resistors, that value is still going to be the same. When we say same, we mean that the current for all resistors has the same value. But if you add more components in there, or if you take out some components, that value will change. It will still be the same for every resistor, but the value will change because that resulting current is because of all those resistors working together. It's a combined effect. Okay. And speaking of that, when we get to parallel, when it's a parallel circuit like this, where you have multiple components connected in parallel, the voltage remains the same. Okay. And we'll explain what parallel is, how to recognize parallel. Voltage remains the same. So how do we recognize parallel? Well, I always like to state that the components are holding hands. We are only dealing with 2-terminal elements. We do not look at any 3-terminal or 4-terminal elements in this class. Okay, so 2-terminal elements means the resistors, capacitors, inductors only have 2 connections. Okay, if each one of those 2 connections is connected to another component with its respective terminals connected together, then we say they are in parallel. Okay, meaning both ends of each resistances have to be connected together, which is what we see in this diagram right here. Okay, so both terminals of each component is connected to each other without any break, then those are said to be in parallel. Okay, both terminals connected together. And again, you can have an infinite number of elements all connected in parallel. It would look something like this. As long as there is no break in the middle, they're all said to be in parallel. In parallel connections, once again, the voltage always remains the same. That voltage is a result of all of those elements working together. It's the combined effect. So if you take out one element or one resistor from that connection, then the voltage will change in value. It'll still be the same for all, but it will remain the same for all components. Okay. So these are important concepts. Okay, where you have a series connection, whether it's a resistor or whether it's resistors, capacitors, or inductors all connected in series, the current through that connection, to that series connection, will always remain the same. When you have components connected in parallel, the voltage will always remain the same. Doesn't matter what component is connected. Okay, very important concepts. The equivalent resistance is simply given by the reciprocal of the sum of the reciprocals. Req is equal to 1 over R1 plus 1 over R2 plus 1 over R3. It's the reciprocal of the sum of all the reciprocals of the resistances in that connection. Okay. If you have 2 resistors in parallel, or 2 resistors, this is only valid for 2 resistors, okay? That Req is simply the product of the 2 divided by the sum of the 2. As easy as that. So it's kind of a nominal shortcut. Okay, if you have 2 resistors in parallel, the equivalent resistance is the product of the two divided by the sum of the two. R1, R2 divided by R1 plus R2. Also, if you have multiple resistors in parallel with the exact same value, then the Req would simply be R over N. If you have N number of resistors in parallel with resistance value R ohms, then Req is simply R divided by N. You can try it out with any value. Take 10 ohm resistors, 2 resistors in parallel, it'd be 10 divided by 2. 1 over 10 plus 1 over 10, 0.1 plus 0.1, 0.2. Reciprocal of 0.2 is 5. 110 ohm resistors in parallel, there will simply be 10 divided by 100. So a couple of shortcuts. Okay, I'm assuming everyone at least has a calculator or at least a smartphone, right? So we are going to solve this and you are going to tell me what the answer is. Okay. So let's take a crack at A first. Take out your calculators. If not, take out your smartphones, use the calculator app. We are asked to find the equivalent resistance between the terminals, the open terminals. So anytime we wish to find total equivalent resistance between any two terminals, we always start at the farthest end. So we start at the farthest end and we move towards our terminals of analysis. We start reducing the circuit from the farthest end. Okay. This approach would work for most circuits. Okay, we start at the farthest end and we start reducing it step by step as we move towards the front. So for example A, not example, sorry, exercise A, we have 4 resistors, right? We can start reducing from the far end and I can see that I have R4 in parallel with R3 in parallel with R2. So I will call that, let's say, R5 is equal to R4 in parallel with R3 in parallel with R2. What do we have? 1 over 2 plus 1 over 3 plus 1 over 6. I heard murmurings of 1 ohm. How much? Everybody concurs. And then Req is, what is the relationship between R1 and R5? Series, because when we reduce R2, R3, R4, well, you already know your stuff. So R1 plus R5, when we reduce the 3 parallel connections into one, they are only connected at the top node with R1. So it's a single connection, not single connection, sorry. It's a node with only 2 connections, so they are in series. So R1 plus R5 plus 1, 3 ohms. Now, I think students would easily be able to do C. So let's talk about B. We start at the farthest end. What do we see? At the farthest end, we have R4. And as we move towards the terminals of analysis, what do we see? The next resistor up is R3. So what is the relationship between R3 and R4? Series or parallel? So they are in parallel, and I can write Req is R4 in parallel with R3. Then comes R2. If we reduce, R3 and R4, let's say R5, you can call it whatever you want. Okay, I'm just using that naming convention, taking it forward. So R5 is the parallel combination of R4 and R3. Then what do we have? Absolutely. We have a series with R2. And then what? In R1. So R6 is R2 parallel, R2 plus R5. So it's in series, and then finally it's the entire network of 3 resistors is in parallel with R1. Let's take a 10-second pause while you go through it. Let me know if you have any questions. Any questions at all? Yes. R6 is just my notation for R2 and R5 in series. No, it's basically just for theoretical analysis. Yeah, it's just it's a mathematical combination of the other 2 resistors, other 3 resistors actually. Because R5 is a combination of R4 and R3, and then R6 is a combination of R2 and R5. So it's the other 3 resistors in combination. Okay, so now I want to show you a technique that would work for most circuits. In that technique, what we do is we take the 2 terminals where we are measuring Req, and we draw them out as horizontal lines. Okay, so let's take example A. I'll call this node 1 and node 2. So 1 and 2. In this technique, what I do is I take all resistors connected each of those terminals and I lay them out vertically. So going from terminal 1 to terminal 2, because those are my terminals of measurement, right? So I would start off with the first resistor connected to terminal 1, and I'm going to draw it vertically going towards 2. You guys with me so far? Okay, terminal 1, R1 is connected to terminal 1. Then R1 is connected to R2, R3, and R4. Okay, so I'm going to draw it out like this. R2, R3, and R4, which at the other end, they're all connected together and going all the way to 2. So drop a line to 2. Now this is a quite simple circuit, so it makes it easy to visualize, right? We already have 3 resistors in parallel. We can see it in the original circuit, but there will be a couple more circuits after this where I will use this technique. So it'll make much more sense. Especially in the homework problem, there are a couple of diamond-shaped circuits, and this technique is particularly useful for those kind of circuits, where it's not quite evident which elements are in series and which are in parallel. Okay, so in this case, again, it's a simple circuit, but let's just use, actually, let's move on to the next and then see. Series parallel analysis techniques, okay? Basically uses the techniques we learned previously, meaning combining resistors in series and parallel, and now we introduce a source in the circuit. Whether it's a voltage source or a current source, it does not matter, but we introduce a source in the circuit, then we use that series parallel analysis reduction technique to solve for the voltages and the currents that appear in that circuit. So in the previous slide, we were determining Req between any two pair of terminals, right? Between a specific pair of terminals. Now, we will look at circuits where a source is already connected. So now the question is, which terminals we use to determine Req? Well, to do that, what we have to do is we remove the source from the circuit. In this case, we have a voltage source Vs. We remove the voltage source Vs from the circuit, and we determine Req from the perspective of the source. Okay, so we have R1, we have R2, and we have R3. So we'll find Req as seen by the source. And so Req between these two terminals, as seen by Vs. So again, anytime you use this technique, you have to remove the source from the circuit, and you determine Req as seen from the perspective of the source itself. So once you remove that voltage source, you now have open terminals. Those open terminals are where you measure, not measure. So if you think of a meter that you're using to measure the Req equivalent resistance, you remove that source and you place a meter in its place. That's what you're doing. Okay. So in the lab, when you do some measurements for resistance measurements, this is exactly the technique you would use. All right. So here, of course, Req is rather straightforward. We have R3 starting at the farthest end in parallel with R2, which is then in series with R1. So how much is it? 1 over, remember, two resistors in parallel. It's the product of the two divided by the sum of the two. Use your calculators and tell me what you get. And let's see if it matches up with my answer. What do we have? You don't even need a calculator for this. 30 times 60 is 1800 divided by 90, 20 plus 10. 30 ohms. Did everybody get 30? Or at least the people who are doing the calculation. So then we plug this Req into the circuit. So I get, my circuit now looks like this. Req is 30 ohms. This is my voltage Vs, 90 volts. And I'm going to say that there is a total current Is that is flowing in the circuit. And that Is, of course, comes from the source. logical direction based on the rules. For a supply, it goes from minus to plus. So it's going up. When it goes up, it doesn't have any other pathway to take except to go right through R1, right? It goes through R1. When it hits the junction, it splits. I can call it I2 and I3. So I1 is the current that goes through R1, I2 through R2, and I3 to R3. Again, it doesn't matter what you choose. You could choose I, A, B, C, X, Y, Z, Batman, Superman, Iron Man, doesn't really matter what name you give that current. It's just a notation. To keep things simple, I just use the convention that is stated in the problem itself. Okay. So IS from Ohm's law can be determined as Vs over Req, which gives me 90 over 30, 3 amps. 3 amps, right? Also, the voltage across Req would be the same as Vs because they're connected in parallel. This, by the way, is a unique circuit. Not this, but anytime you have a source connected to a single load, it's a unique circuit. Is it in series or is it in parallel? I heard someone say series. How many for series? How many for parallel? Nobody? How many for both? The answer is both. So that's why it's unique. It's in series as well as in parallel, which means the two rules that we just talked about, the voltage across that parallel connection remains the same, and current through a series connection remains the same, are both valid. Current for the source is also 3 amps. Current for the Req, rest of the circuit, is also 3 amps. Voltage for the source is 90 volts. Voltage for Req is also 90 volts. So those two rules still apply. Again, keep in mind, this Req is a mathematical representation of the 3 resistors. It's a mathematical representation and real life electrical equivalent. Okay, real life electrical equivalent. Physically, it's 3 separate connections. The source sees it as one single resistance. So now we reduce the entire circuit down to one Req, one single Req. Now we expand it back up again, one step at a time. Okay, so when we expand it again, I can say this is, of course, the parallel combination. Let's call it R4. We hadn't defined it earlier, but let's call it R4. R4 is the parallel combination of R3 and R2. Okay, which was what? 20 ohms. So this is 20 ohms, and this is 10 ohms. IS is flowing through both the 10 ohms as well as the 20 ohms. So now you tell me what is the voltage across those resistors from Ohm's law. I can write VR1 is equal to IS times R1. Don't you need a calculator for this? And VR4 would be IS times R4. So what is the voltage? 3 amps going through 10 ohms. 30. How about VR4? Does KVL verify your answer? Yes, it does. 90 volts minus 30 minus 60 is equal to 0. So always use KVL and KCL to verify your answers at the end. Okay. And from here, I can also find IR2. IR2 is, of course, 60 divided by 30. So 2 amps. And IR3 is 60 divided by 60. Gives me 1 amp. 2 plus 1 is 3 amps. KCL tells me that my answer is correct. Okay. So I2 is 2 amps. This is 1 amp. This is 3 amps. What do you notice about the voltage relationship with the resistances and the current relationship with the resistances? So this was 10 ohms. That gives me a voltage of what? 30 volts, right? So go back up there. 30 volts. And this is 60 volts. Note the polarity. If current enters the junction for a passive component like a resistor, current flows from high to low, meaning point of entry of the current is plus, point of exit is minus. The voltage drop across each resistor is directly proportional to the value of the resistor. The higher the value of the resistor, the higher the voltage. Lower the value, lower the voltage. So a 10 ohm resistor has only 30 volts, whereas the 20 ohm resistor has 60 volts across it. Current is the opposite. Current is a result of the resistor value. So the higher the resistance, meaning the higher the opposition, the lower the current. And the lower the resistance, the higher the current. So a 10 ohm resistor will have less opposition to the flow of current. We have 3 amps going through it. And then the 30 and the 60, we have 2 and 1. So it's inversely proportional. Keep these concepts in mind. So when you solve larger circuits, you obtain a value, you should immediately think of these concepts to verify your answers. One final thing, there's still 2 minutes left. One final thing about series and parallel. Our brains automatically do not question a REQ for a series connection. If it's 10 plus 10 plus 10, what is REQ? What is 30 in relationship with 10? It's higher, it's bigger, right? Our brains automatically deducted, we never even question it. Resistors in parallel. If you have 30, 30, 30 in parallel, what is the resulting REQ? Should be 10. 30 divided by 3, 10. Now your brain needs to be trained to think, if it's a parallel connection of resistors, the resulting REQ will always, always, always be smaller than the smallest value in that network. If it's 10 plus 20 plus 30, where did we see that? 6 plus 3 plus 2 in A. What did we get? 1 ohm. 1 is smaller than the smallest resistor in that circuit, 2 ohms. If you get a value that is equal to or larger than 2, then your answer is incorrect. Your brains need to be trained to think that. Okay, so these are small concepts you need to keep in mind as you go along in circuit analysis. As a working professional engineer, these small concepts will hold you in good stead. Okay. All right. There is a homework due tonight. I think it's resistors in series and parallel. If you get stuck anywhere, if you have any questions, you let me know. And then also we will look at these examples on Wednesday, but that homework is due on Wednesday. So get started on it because I already did an example in class. Again, if you have questions, reach out to me. I will have student hours this afternoon. So again, stop by my office. I'd be more than happy to answer any questions you have.